So my name is Nathan Odges, and I've been leading the project around improving land characterization with LiDAR. Um, right. And so when we talk about land characterization, you might also be familiar with terms like terrain analysis or geomorphometry. What we're really talking about is using digital elevation models to, I guess, measure the shape of the terrain, the landscape. We do that by computing what we call topographic parameters. So things like slope, aspect, which is the direction that a piece of land faces, lots of different kinds of curvatures of the landscape, sometimes some indices that tell us about how exposed a piece of land is, many parameters that tell us about how water moves through the landscape, and where the different kinds of landforms are and things like that. And I suppose of this list, Council was particularly interested in slope and having a better map of slope to help inform policy and land management decisions. Mathematically, and so that's what this talk's going to be about today. So mathematically, slope is one of the most important topographic parameters. I say that because it's the first derivative of elevation mathematically, and so what that means is it's talking about the steepness of the land in the direction of steepest descent at a given location. Um, in addition, it's an important influence on many biophysical processes occurring in the landscape. For example, through its effect on the velocity of water movement, its influence on the rate of infiltration of water into the soil and therefore the soil water content. He's already talked a little bit about the potential for erosion to occur. Um, and also, it's got an influence on the expression of aspect-related effects on microclimate. And what I mean by that is, in the southern hemisphere, I suppose we tend to think of north-facing slopes being warmer and drier on average than south-facing slopes. And to some extent, the 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 s- the the strength of those aspect-related effects depends on how steep the slope is. Those effects tend to be magnified as slope becomes steeper. And I put this up here just to um, illustrate the point that it's not too much of an overstatement to say that the LiDAR elevation model is a bit of a step change in terms of how the level of detail with which we can resolve the shape of the topography. So obviously, on the left-hand side, a 5-meter elevation model, and on the right-hand side, the same area, but drawn from our national 25-meter legacy elevation model, on the right, derived from contour lines, and it's pretty easy to see that with this there's a lot more resolving power on the left-hand side, especially in some of the in the lower relief parts of the landscape along streams, stream terraces, and things. Um, Much more able to pick these things out on the 5-meter grid than on the 25-meter grid. Um, in terms of applications of slope, a couple of big ones at the moment. Slopes embedded in the idea of land use capability assessment, and it's also part of the intensive intergrazing rule. So we'll touch on these a bit more detail now. Land use capability, of course, talking about the categorizing land. Um, with respect to its potential for long-term sustainable production, and that takes into account the 5 physical factors of rock type, soil, slope angle, erosion type and severity, and vegetation cover. Slope is present in the classification through a class, a slope class. We'll come back to that shortly. And then the intensive intergrazing rules, talking about, land that is used for intensive intergrazing must be 10 degrees slope or less, as determined by measuring the slope over any 20-meter distance of the land. We'll talk about that again in a minute too. I thought I'd touch briefly on how do we compute slope. And I will say with this work, we had two digital elevation models derived from the region-wide LiDAR coverage, one of those at 1 meter resolution and one of those at 5 meter resolution. We applied the same approach to each. We computed the slope in degrees using a conventional moving window approach. If you're familiar with doing similar sorts of things in ArcGIS or any of the common GIS software packages. And what that really means is for every cell in the LiDAR grid, to compute the slope, it's looking at a small window or neighborhood of grid cells around that cell, and accounting for the rate of change of elevation across the neighbors in the X and the Y directions. And it's a moving window because we're using that. We do the same thing for every grid cell in the grid to estimate the slope. The size of the moving window is important. I've put down here, so the size of the moving window is important. We set it up to use a 20 meter by 20 meter moving window. That's our best simulation of the slope required for the implementation of the intensive winter grazing rules. And on the 1 meter elevation model, that means using a moving window of about 21 by 21 grid cells. On the 5 meter elevation model, that means a moving window of 5 by 5 grid cells. I'll touch briefly on this. I'll say that that's not the same as resampling the DEM to a 20 meter resolution and deriving slope just from that layer. Because if we did that on a 20 meter grid, the smallest window that you could use is 3 by 3 grid cells. And that's really a 40 meter by 40 meter footprint, which is too smoothed really for what the intensive winter grazing rules need anyway. This slide really quickly just illustrates that smoothing effect on the 1 meter elevation model. So on the 1 meter elevation model, using a moving window of 3 by 3 grid cells on the left-hand side there, 20 meter in the middle, which is what we use in this project, and on the right-hand side, a 100 meter moving window. Just illustrating that the point that the size of the moving window has a smoothing effect on slope and other attributes derived using that kind of approach, which allows you to tailor, I guess, how you compute slope and other terrain attributes for that matter for specific applications. So if you're working at a really hyper-local scale, let's say, and you're interested in pulling out, where are the road cuts or where are the drains or where are the breaks of slope very precisely, you might want to use a really small moving window. For this application, because the rules are talking about a slope over a 20 meter distance, I guess we're thinking more there of kind of like a field scale, almost a paddock scale of measurement of slope there. So we've got when we've got our map of slope in degrees, then we can classify that map of slope into the classes that the slope classes required for LUC implementation. So for example, 0 to 3 degree slope is class A, 4 to 7 degrees is class B slope, and so on. So we can map out the LUC slope classes by doing that. In a similar way, we can map out the slope classes for the intensive winter grazing rules, 0 to less than 10 degrees or less than or equal to 10 degrees. Notionally grazable in winter, everything else over 10 degrees, not grazable in winter. Bring you through to some results, and so yeah, this is a map of slope gradient for the region, and some detail view there on the right hand side. And I guess what that's just illustrating is how smoothly the slope in degrees varies as you move across the landscape. Obviously tends to be steeper in the hill country, much less steep on the lower relief areas, as I suppose we'd expect. You can start to see where some of the terrace edges are and things like that in the low-lying parts of the landscape as well. If we go through to the LUC slope classes, it's probably difficult to tell, but you can start to see on that right-hand image there, where instead of a smoothly varying slope, it's aggregating those slopes up into the classes. So you've got broad areas in some places of sort of a single color. So you're talking about class B or class C slopes all the way through here, sort of thing. And then finally, the intensive winter grazing slope class map, same area, and you can see obviously most of the hillier country is greater than 10 degrees. The less than 10 degree land tends to be on the lower parts of the landscape, but you can see it pulls out some small areas along some of the ridge tops and things like that as well. Drawing to a bit of a close. So I will say what we achieved here, we've achieved 3 sets of slope maps at two grid resolutions, 1 meter and 5 meter. And I've got here, and I think it's important to note that these maps are a starting point for use in a range of applications like mapping LUC, like implementing intensive winter grazing rules. And I say that because it's probable that further analysis, interpretation, or context may be required to inform their use. For example, as I mentioned up here, we've got some less than 10 degree land right up on the ridge tops, which, notionally you could graze, but actually maybe they're too small of an area, or more likely in this case, access is just not going to work. So you may need to draw in some other pieces of supporting information to really help you apply these kinds of maps to use cases. But I do hope this illustrates some of what we can do with terrain analysis on LiDAR, and yeah, I guess the benefits over our sort of legacy products, which are at a much coarser resolution. I'll stop here, and I'm happy to answer questions. Thank you.
Ngā mihi, Nathan. We have a question from Mark Crawford. He asks, hi Nathan, 10 degrees is not grazable, just not permitted activity and would require consent, I would assume. Are you able to comment on that?
I'm not able to comment on that. No, we're just trying to apply the rules as written. If there are exceptions, then that's entirely possible, I guess. You'd want to look at, or it could be useful to create a different classification of the map that captures some of those edge cases. I'm not sure, but once we've got the map of slope gradient, then we can kind of do whatever we want with it in that sense, pulling out other classes that may be of use. Yeah.
There's no other questions in the chat. Does anyone? I think everyone else is muted. Just a question from me then. What do you see as sort of the next step in this field after this?
Good question. I think partly it's about identifying what are some other important use cases, and what kinds of derivatives of the elevation model do we need to sort of service those. Yeah.
Thank you for that. There's another question from Anna. Are there any plans to update the legacy products based on a high-res LiDAR?
Plans to update the legacy products. I can say that the slope class map that we've created is contributing to a revised or an updated land use capability layer for Hawke's Bay. I don't think we're talking about that today, but I believe that's in the works. That's all that I'm able to comment on, I think.
Oh, another question just appeared. So I'm just reading them as they come through. Do you see all councils across New Zealand needing to use LiDAR to update their LUC 1 to 3 land for NPS HPL?
Good question. I think it just gives you that much more power to pull out the variation in the topography compared to our sort of legacy elevation models. So I mean, I think you probably don't need to use a LiDAR sort of scale grid, but um, I think it just, yeah, I think it just allows you to have that much more detail. You still may need to, and as I said, I mean, you still may need to aggregate up that LUC slope class map into sort of manageable units, all the really tiny bits of slope that are, really small areas. You might need to aggregate them out. But if you're starting with a really high resolution product, then that lets you do that in a I suppose in a way that you can't do as well if you're starting from a coarser resolution elevation model. Hopefully that answers the question.
Got another question coming in. Are there plans to apply these analysis nationwide for areas that have sufficient LiDAR coverage?
I'd love to do that, but I'm aware that councils have got their own LiDAR and they may be doing things like this themselves already. Yeah, I'm not too sure.
All right. So thank you so much for fielding all these questions.